Hello and welcome. In this video, we will see how to use integrals to calculate hydrostatic force. If an object is submerged in liquid, the liquid exerts a pressure on the object, which results in a force across the entire object. So we want to understand these two ideas of hydrostatic pressure and force. First of all, hydrostatic pressure, which we'll denote by P, is the fluid force per unit area. And the formula for hydrostatic pressure is mass density times acceleration due to gravity times the current depth that the object is submerged in the fluid. If we are working with metric units, the mass density will typically be measured in kilograms per cubic meters. We have a mass divided by volume, and then acceleration due to gravity is meters per second squared. If we're using imperial units, then typically the measurements are given in pounds and feet, and so rho times g will be a weight density, and we'll be given that value together. And this will typically be measured in pounds per cubic foot. So with imperial units, we do not have to multiply by the acceleration due to gravity. Hydrostatic force is the total fluid force exerted on a submerged object. The formula for hydrostatic force is P, that's pressure, times the area of the object. And we're assuming here that the object is horizontal. So we have a horizontally submerged object, so that the depth is all the same throughout the object. In previous sections, we often thought of force corresponding to weight. That is not the case here. Force is not weight here. Force is the fluid force exerted by the fluid on the submerged object. Let's summarize the units for hydrostatic pressure and hydrostatic force. Hydrostatic pressure has units of force per area. So in the imperial system, typically we're measuring in pounds per square foot. In the metric system, force per area will be measured in newtons divided by square meters. For hydrostatic force, we simply have force measurements. The imperial measurements are typically pounds, and the metric measurements typically newtons. Let's work through a few examples. The deepest part of the ocean, the Mariana Trench, is approximately 11,000 meters deep. It's actually a little bit deeper than that. And we'd like to know what is the hydrostatic pressure at this depth. And we will use 1,000 kilograms per cubic meters for the mass density of water. Well, the formula for hydrostatic pressure is rho, that's mass density, times the acceleration due to gravity, times the depth. And we want to keep track of units here to make sure that we end up with units of newtons per meter squared at the end of this calculation. So the density, that's 1,000 kilograms per meters cubed. We multiply by acceleration due to gravity, 9.81 meters per second squared. And then we multiply by the depth, and that is 11,000 meters. Let's keep track of units now. 1,000, that's the density, kilograms per cubic meters, 9.81 meters per second squared. And 11,000, that has units of meters. Kilograms times meters per second squared is a measurement of newtons. That's the force in metric. And then we can cancel a meters with the meters here and have meters squared. So we have newtons per square meters. Those are the units that we want for pressure. Multiplying these numbers together, we have approximately 1.08 times 10 to the 8 newtons per meter squared. Newtons per meter squared has a special name. This is called pascals. So pascals, that's the same as newtons per meter squared. That is the metric measurement of hydrostatic pressure. Let's take a look at the second example. What is the hydrostatic pressure at the bottom of a 3-foot tall drum that has oil that weighs 720 pounds per cubic foot? This is a weight density. A weight density is rho times g all taken together. So we still have the same formula for pressure. Pressure is mass density times acceleration due to gravity times depth. So to solve this problem, we simply multiply 720, that is pounds per cubic foot, times the 3 feet of depth. And let's again think of the units here. We have pounds per cubic foot times units of feet. We can cancel some feet here, and we have pounds per feet squared. So the final answer is 2,160 pounds per square foot. It's very important here to make sure that the units work out. Pressure is always measured in force per area. So in metric, it's going to be newtons per meter squared. That's also called pascals. In imperial, it's pounds per square foot. Typically with imperial, we are given a weight density, which is rho times g. We do not multiply by 9.81 meters per second squared when we are dealing with imperial units. Now that we've seen some examples with hydrostatic pressure, Let's take a look at an example where we calculate hydrostatic force. Here we have an aquarium that is 2 feet wide, 4 feet long, 3 feet tall. And we're told that it's full of water that has a weight density of 62 pounds per cubic foot. Notice that we are using imperial units. We will not be multiplying by 9.81 to get density here. We want to know what is the hydrostatic force exerted first on the base of the tank, and then what's the hydrostatic force exerted on one of the 3 foot by 4 foot sides. So first of all, let's write down the formula for hydrostatic force. Again, this is different from weight. The force here is the force exerted by the water. Force equals pressure times area, and the formula for hydrostatic pressure is mass density times gravity times depth, and then we multiply by the area. Well, the area is literally just the area of the base of the tank. That's 4 feet by 2 feet. So area here is just 4 times 2. Rho times g, that is the weight density taken together, that is the same as the 62 pounds per cubic foot. We do not multiply by 9.81 meters per second squared. So rho times g, that is 62. The depth here is the same. The depth is how deep the aquarium is, which is 3 feet. So we multiply 62 times 3 times 4 times 2. This equals 1,512. And let's think now about units. 62, that's pounds per cubic foot. And 3, 4, and 2, these are all measurements of feet. So we have pounds per cubic foot times feet cubed. The measurement here is in pounds, which makes sense. We are calculating a hydrostatic force, so we would expect the measurement to be in pounds. Keeping track of the units for these problems is crucial to make sure that you're on the right track and solving the problem correctly. Finally, let's take a look at the second part of this problem. We want to know the hydrostatic force exerted on one of the 4 by 3 sides of the tank. How can we solve this? Well, let's go ahead and draw this 4 foot by 3 foot side of the tank. Looks something like this. We would like to use the formula force equals pressure times area, but we can't just apply this formula as is. Why not? Well, the depth is changing throughout this side of the tank. At the top, the depth of the water is 0, and then we have 3 feet of water at the bottom, so we don't have a constant depth. We cannot simply use the formula force equals pressure times area in order to calculate hydrostatic force in this example. So how do we solve this? The answer is an integral. We are going to find a representative slice of the side of the tank. We'll compute the force on that representative slice, and then we will integrate to find the total force. We've seen this concept before with volume and also with work performed. We'll have a very similar sort of idea here. So let's draw in a representative slice of the side of the tank. And let's calculate how much force is being applied on this representative slice. We'll say that this is a depth x from the top of the tank, and the thickness of this slice, well, it's some small change in x, so it's dx. And we want to find an expression for the force exerted on a slice. If we can find an expression for that, we simply integrate to find the total amount of force. Well, force on a slice, now we can use the good old formula force equals pressure times area, because the depth is all the same, the depth is just x. So pressure here, that is rho times g times the depth times the area, and the area here, well, we have a little rectangle. It's a 4 foot long rectangle that is dx feet wide. So the area is 4 times dx. The depth d is just x, and rho times g is the weight density. So we have 62, that's rho times g, times the depth, x meters, times 4 times dx. That's how much force is applied to this slice. Since this is just the force on a slice, we'll go ahead and call this dF for the force on just a slice. Let's think of units here. 62 is pounds per cubic foot. X, that's measured in feet. 4, that's the width, that's measured in feet as well. And dx, that's again a measurement of feet. So if we cancel these units, we have units of pounds, which we expect for the units of force. So we are on the right track. Now that we have the expression for the force on a slice, the total force is just the integral. Total hydrostatic force here is the integral of 62 times x times 4 dx, and we're integrating in terms of x. So what are the limits of integration so that we get all of this side of the tank? Well, x is the measurement from the top of the tank, so we start with x equals 0 all the way down to a depth of x equals 3. So the limits of integration are from 0 to 3. We won't take the time to work through this integral by hand, but notice that it should be a pretty easy one. 62 times 4, those are just constants. So we're integrating a constant times x. We could very easily find the antiderivative, plug in the 0,3, take the difference, and we would get the answer here. This works out to be 1,116 pounds. That is how much force is applied by the water to one side of this aquarium.